In this video, we're going to be discussing how to solve this quadratic equations manipulation problem from AOP's Algebra 1 homework. This is a pretty moderate difficulty level problem that requires you to shuffle around and manipulate an equation that you know how to solve in order to find the roots or the zeros of the quadratic equation. So the problem statement says, find all values of x such that this equation, 6 equals 35 over x minus 49 over x squared, is true. So we're trying to find the values of x to satisfy this equation. So before we go any further, let's review what a quadratic equation is, because that's what we're trying to get this into. We can't really solve this equation with elementary distribution and linear equation solving techniques, because we've got this big x squared here that's going to be hard to deal with. So we first need to get this into the form of a quadratic equation. And just as a review, a quadratic equation is any equation of the form ax squared plus bx plus c equals 0. A quadratic equation will always be equal to 0 here. We'll always have a degree 2 squared x term with coefficient a, and then a linear term, x with coefficient b, and a constant term c. So that is the form of quadratic equation there. Alright, so now that we know what one looks like, let's go ahead and set to work on figuring out how to convert this rather strange looking equation into a regular quadratic form. So we've got some ugly looking fractions right here. These are going to be pretty hard to deal with. So the first thing we're going to want to do is get rid of this x squared, since it's the easiest one to deal with first. So to get rid of a fraction, we have to multiply both sides by its denominator. So in this case, we must multiply both sides by x squared. Doing this, we would get 6x squared, that's what 6 times x squared is, equals x squared times 35 over x minus 49, because the denominator of this fraction is gone now. Okay, so this is looking a little bit better. We still have one fraction in here. We can simplify this portion here by multiplying straight across. We would then get 6x squared equals 35x squared, just multiplying right across, over x equals minus 49. Okay, so this equation, like I said earlier, still looks a bit ugly. We've got this x here that we'd like to move. So how do we do this? Well, what we can do here is to solve this issue. We can use the exponent laws. So this 35x squared over x, we can treat this as temporarily ignoring this constant term 35, and just treating this as x squared over x for the time being. Now, the exponent law of dividing powers states that when you have two powers with the same base, in this case x, dividing each other on a fraction, you can subtract the powers. Please note there's an invisible 1 here. Everything has a 1 there. So what we can do here is we can subtract the powers since these have the same base of x. We have x squared over x to the first. That's 2 minus 1, which is the same as x to the first, or just x. Okay, now that we've dealt with that, we have a radically simpler quadratic equation, or close to one anyway. We have 6x squared equals 35x. The fraction just goes away because we converted this to x, minus 49. Okay, now we've gotten drastically closer to attaining that quadratic equation form. The only thing missing is that this does not equal 0. We need everything to be on one side of the equation and everything else to be 0. So our aim is to get the 35x and the negative 49 all on the left side, so that we're left with 0 on the other. So this is pretty simple. All we have to do is do some simple manipulation. 6x squared, subtract the 35x off from both sides, equals negative 49. Then, to complete this process, we can add 49 to both sides. Get 6x squared minus 35x plus 49 and equals 0. So this is our final manipulated version of the quadratic equation. We finally got this thing worked out. So now, the next step is to solve this thing. So in order to solve a quadratic equation, we need to factor it. And by factoring it, we mean to write it as a product of two binomials. And in this case, this is a non-monic quadratic, meaning it's not of the form x squared, it's 6x squared. There's a constant coefficient here that we must take into consideration. So when we factor this, we're going to have two binomials. I'm just going to write the parentheses here as a skeleton form. So we're going to have an x squared, which means we have two x's, and we have a 6 coefficient. So in this case, what we're going to have is, since 3 times 2 equals 6, that means those are the two coefficients of x that we need. That's the only one that will work for this equation. That's how you factor an equation. You look at this coefficient term here, and you find out what two coefficients of x you need to get to this coefficient over here of 6. In this case, it's 3 and 2. So one of them is going to be just having the x term, and for example, 3x. And the other is going to be 2x, obviously, because 3x times 2x is 6x squared. So we've started off here with our factorization, and now we've got kind of a mystery here. This kind of blank. We've got to fill in the blank. And that's kind of the central idea of factoring a quadratic. We want to find out what numbers must go in these blanks in order to satisfy this equation when we multiply it through. So we've got a 49 here. This is our constant term. So what this tells us is we need two numbers that multiply to 49. That's pretty much all we need to know about this quadratic, because 49, the only two numbers that can multiply to 49, 7 and 7. And we've got positive here, which means we either have a positive 7 and a positive 7, or a negative 7 and a negative 7. So what happened here when I was originally solving the problem is I started off with using positive 7 and positive 7. However, this didn't work, because when you multiplied this through, I didn't get negative 35x, I got positive 35x, because both constant values were positive. That's why, when you're looking at this, what you can say is, oh, this is negative. That means both of the constant terms we put in these empty spaces, they can't both be positive. They have to be negative, because we got this negative sign here. That's why that leaves only negative 7 and negative 7 as reasonable values here. So this is our factorization. We can then test this by using the distributive property to multiply this out. So first terms, 3x and 2x. As we know, that's 6x squared. Then outer terms, negative 21x minus 21x. And then inner terms, minus 14x. And then last terms, positive 49. Okay, we've got some like terms here we can combine. So negative 21x minus 14x, this is just simply negative 35x. Do this, plus 49. And we can confirm this matches right back up with our original quadratic equation, and we have successfully factored this quadratic. So, let's clear some space here. So now that we've factored this equation, the next step we need to take from here is the final step actually, is to find the roots. In this case, the values of x that make each of these binomials here equal to 0. So to do this, we can write a simple linear equation. 3x minus 7 equals 0 for the first one, where we need to solve for x. To do this, we can isolate x. 3x equals 7 by adding 7 to both sides. Then x equals 7 over 3, dividing both sides by 3. We can do a similar thing for the second binomial, because there are always going to be, in most cases anyway, two solutions to a quadratic. Same thing over here. We just write a simple linear equation, isolate the x, divide both sides by 2, and we have x equals 7 over 2. So there you have it. We've got our two values of x here that satisfy this quadratic equation. These are sometimes called the roots or the zeros. X equals 7 over 3 and x equals 7 over 2. This is indeed what the question asked for, all values that satisfy the equation. And that's pretty much it for this question. We used a manipulation technique to get this equation into a familiar quadratic form, and then we factored it in order to find the roots of this equation. Alright, this was a quadratic equations manipulation and factoring problem from AOPS Algebra 1.